right, let's get started. I'm going to get the sign-in sheet passed around. I figured this was an appropriate image to put on the slide considering the blisteringly cold weather we're experiencing today, right, in the middle of February. Because, I mean, what's the high supposed to be today, like in the 70s? 75 in February in West Virginia? And it's supposed to, didn't somebody, hear somebody say it's supposed to be like 78 or something later this week or something? 80? Sorry. Wow. I didn't wear a jacket or a sweater or anything today. I wore this, and I think I even went a little overboard. Okay. Let's talk a little bit about the schedule and what's going on. All right, so attendance grades, I went ahead and updated all of the attendance grades on Blackboard. So everything up until, obviously, today's lecture is up to date. Homework 3 is still being graded, but the solution should be up. So that should be available for you all to download. My hope is to get that back to you all on Wednesday. And then on Wednesday, you submit homework 4. I give you the solution. So again, no late submissions on homework number 4. We do our exam review on Wednesday, and then we have our celebration on Friday. So I guess I should ask, are there any questions about the homework assignment, which is due on Wednesday? You can ask what the answer to number 1 is. I'll answer it, but... And that would be an involved thing to even describe just what's the answer, because it's not like the answer's 4, you know. There's, you know, you got dimensions and efficiencies and strain limits and all that. Yes, sir.
The material for homework 4 is going to be like...
Is what?
The material that's on homework number 4 that is going to be on plus 1 or is that...
Yes.
Okay.
Yes. No, the exam review slides are also already on Blackboard, so you all are free to download those at any point. Any questions? All right. Do me a favor, on Wednesday, come prepared to ask questions about the exam, okay? Another thing about this exam, and this is totally dependent upon your schedules, but this room is open before the exam. Like, there's nobody in here from 9 to 10. Now, I'm not saying we can start the exam, bless you, I'm not saying we can start the exam at 9, because I'm sure there's folks in here that have class before this one. However, we can start a little early, okay? Fine to start like at 9:55 or something like that. However, you also have to recognize that right after this class, there is another class, and they also have their exam on Friday. So like, we can't like push it too far because they got to get in and get ready for their exam, okay? So I guess my point is, on Friday, be here on time because you have a celebration going on. So, sound good? What? There'll be party favors. The exam. All right. Any questions? Okay, so we kind of started to discuss this near the end of class last time, and I thought I would take it a little slower. I think that this is an incredibly important set of notes to go through the design of T-beams, and I really sort of like these topics, T-beams and double reinforced beams, because they really sort of lock in just regular basic reinforced concrete design. Because if you understand this, then the design of a simply or singly reinforced rectangular concrete beam should be child's play compared to this. So I really think it sort of stretches the concepts a bit. Now, this is the design of a known cross-section. We're in known cross-section territory. We're not looking at an unknown cross-section. And the reason why is because usually in T-beam design, the beam and slab components can be sized separately. So really the main task is to select the amount of reinforcement. Now, hold on. Okay. Now, we looked at 2 previous examples where we looked at a rectangular T-beam and a true T-beam, we know by now from an analysis standpoint that analyzing a rectangular T-beam versus a true T-beam, I mean, the depth of the stress block, that's really what makes it complicated. In other words, if you have a stress block like in the upper scenario where the stress block depth is less than the flange height, then it's nothing more than ASFYD minus A over 2. The analysis isn't that complicated. And if the analysis isn't that complicated, then the design isn't complicated either. Okay, that's pretty straightforward. All right. Now, that is the issue with a rectangular beam. With a true T-beam, the analysis got a little more complicated because the geometry of the stress block got a little more complicated. And what we did in our analysis example, if you recall, was this. We split the T-shaped stress block into a flange couple and a web couple, and we're gonna dig into that here in a second. But let me start here. Okay, so in design, when we're talking about T-beams, again, our goal is to try and determine the amount of reinforcement required in a T-beam. Okay. So the first thing that we're going to do, I mean, we're going to have to assume a phi value and all that, like I understand that. But in general, our design philosophy is going to be as follows. The first thing we're going to do is we're going to assume that we are dealing with a rectangular T-beam. Okay, that's going to be how we approach this. We're going to start off assuming we have a rectangular T-beam. So if we have a rectangular T-beam, this is how much reinforcement is required, because that is the required amount of reinforcement for a rectangular cross-section. It's no different, okay? All right? Now, recall, if the section is rectangular, what that means is that A, the depth of the stress block, is less than or equal to the flange height, okay? That's what a rectangular section means. So this is what we're going to do. The first thing we're going to do is we're going to calculate a rho value, and that rho value is going to be based on the assumption that we're dealing with a rectangular cross-section. Then we're going to take that rho value and we're going to say, all right, if that is the reinforcement ratio that we were going to use, if that's the case, then tell me this. Using that reinforcement ratio, what's A? Okay? So that's going to be the next step, is we make an assumption that we have a rectangular T-beam, and then we calculate A to see whether or not that assumption is valid. Now, if it is valid, great. We just design this as if we did, I think it was like example 7 or something, like the known cross-section. Just design this accordingly and just move on. However, if we are dealing with a true T-beam, if that relationship doesn't hold, then our mathematics gets a little more complicated. Now, we can simplify that, though, a little bit, because if you look at this discretization of a T-beam's flexural capacity, remember we have the flange web couple, and we have, or the flange couple, and we have the web couple. Now, if you look at this, we can determine the flexural capacity of any T-beam as long as we have one dimension, and that's A. But that's really sort of the primary unknown. We're going to sort of get that in a roundabout way, and I think you're going to see how this works. Okay, so let's look at this. Okay, would you agree with this statement that ultimately we can express the capacity of a true T-beam as follows? The capacity of the flange couple plus the capacity of the web couple. That's exactly what we did in our previous example, right? We had a nominal capacity of the flange couple, nominal capacity of the web couple, and then I've got my phi values thrown in here because we're going to need to adjust those by our strength reduction factor. So far, so good? Okay. All right. Now, we're going to the way that we're going to do this, if you look at these two couples, and the reason we discretize this as follows, if I give you any random T-beam, and let's say you know it's a true T-beam, then the only variable that you need to determine the flexural capacity of that beam is A. So if you look at this couple here, there's nothing here dependent upon A. I could determine the nominal moment capacity of the flange couple right now. So what we'll do when we have a true T-beam is we'll determine the capacity of that first, and then figure out, well, how much web couple capacity do we need to meet overall requirements. Just if that seems a little convoluted, don't worry, just bear with me. I think you'll see how this goes. Okay, let's take these equations. Let's just sort of slowly digest them and make sure we understand what's going on. Okay, So you agree that the nominal moment capacity of the flange and the nominal moment capacity of the web, you can add those together to get the whole capacity of the whole thing. All right? Well, let's take this. Let's take this first one. This is the nominal moment capacity of the flange couple. And remember, how do you do a moment capacity in general? It's just a force times a distance, right? So the force, we went with the compressive force here, and it was the compressive force in the flange times that moment arm. What is that compressive force? Well, it's 0.85 FC prime times this area. And what is the area of this shaded region right here? Well, it's the height of the flange times that total width, which is B minus that B sub W. Make sense? Okay? For the web couple, compressive force times moment arm. Oh, let me go back to the flange couple for a second. The moment arm. Moment arm, how do we get that moment arm? We have D minus half a flange height. Make sense? All right. For the web, what do we have? We have 0.85 FC prime times this area, ABW. That's what we got here. And the moment arm, D minus A over 2. Does that make sense? Everybody with me so far? Okay. What did I hit the screen blank button. Okay. Okay. Now, let me go back to this. Okay. Remember that compression has to equal tension, right? Now, let's look over here on the left. Okay. How do we get this depth A over here on the very left? Like, how do we get that? Well, that depth A is that magical number, it's that magical depth that is required so this compressive force equals whatever tensile force you're getting from this steel. Make sense? Okay, well, the same thing has to hold true for over here and here. Like, for instance, if I look at this flange couple, okay, 0.85 FC prime times the area right here will give me some compressive force. Let's say it's, I don't know, 300 kips. Okay? There's got to be some amount of steel that matches that 300 kips. Make sense? Okay? So I propose that for each one of these couples, you have a compressive force, but you got to have a matching tensile force. If you have a compressive force, you got to have a matching tensile force. So the idea is that in order to determine the total amount of steel required, what we'll do is we'll figure out essentially how much steel we need here, how much steel we need here, add them up, and then pick a pattern based off that sum. And it's pretty much that simple, okay? Make sense? Now, the way that we do that is this. For the flange couple, it's pretty simple, okay? We still have our fundamental relationship that C equals T. So do you agree with this expression right here up top? So 0.85 FC prime times the area of this has got to equal ASFY. But instead of ASFY, we're basically saying AS for this flange steel couple. Make sense? Yes.
Last week when we figured out that it was equal to it, we can't do that all the time. Just skip that step in that example.
Okay, I get what you're talking about when we added up the C's and compared the C's and T's.
Yeah.
We didn't need to do that for that specific example. What we're doing here is we're sort of using that principle in a roundabout way to go back and solve for the area of steel. See, in design phase, we don't know what the area of steel is. That's our goal. Does that make sense? Okay. And don't worry, I know that the steps might seem convoluted, but we'll have some practice on this. So far, so good? Okay. Now that's for the steel couple. For the web couple, what we do is this. We say, well, phi mn has got to be greater than or equal to mu, and phi mn is whatever this capacity is plus whatever this capacity is. So because we don't really know what A is because we're in design mode, what we can do is figure out, well, how much nominal moment capacity do we need from our web? And if we figure out how much capacity we need from this, we can just use essentially this equation to solve it out. So I'll walk you through step by step how this works. And if you're thinking, oh, God, this is horrible, don't worry. It's really not that bad. I think you'll find as we get into this, it's pretty straightforward. So step one. Step one, we need to compute the factored moments on the beam. So this is looking at self-weights and so on and so forth. One of the things I will mention, just like with a known cross-section, the self-weight of the beam is known. So because of that, we don't need to assume a self-weight because we know what the cross-section looks like. Now, step 2, we do have to assume a phi value, so that's something we'd have to go back and check. Now, third, we're going to make an assumption that the neutral axis is in the flange. So what I mean by this here on step 3, we are assuming a rectangular T-beam, okay? That's what this means right here. So we're assuming that the beam is rectangular. If the beam is rectangular, that's your required reinforcement ratio. Then we take that required reinforcement ratio and we say, okay, what would the depth of the stress block be if we use that? Now, if that depth A, if it's less than or equal to h sub f, then our assumption was correct. And we do have a rectangular T-beam. We just go on to step 5. If not, then we skip a few steps and we go on to step 8. So step 5 is where rectangular analysis takes off, and step 8 is where true T-beam analysis takes off. Does that make sense? Now, for step 5, if you look at this, this should look pretty familiar because that comes, copy and paste from the known cross-section notes, and that's because it does. If you have a rectangular beam, get your area of steel, rho BD, pick a pattern, and go with it. Okay? Pretty straightforward. Okay? If you've got a true T-beam, here's what you do. If you got a true T-beam, figure out how much steel you need for your flange steel couple, figure out the moment capacity, you got your factored loads, got your flange capacity, divide out to figure out your web capacity, calculate a reinforcement ratio, calculate steel, add it up, select. Seems convoluted. Promise you, step by step, it's actually pretty straightforward. Before we get into an example, does anybody have any questions from a conceptual standpoint? Yes. Yes, because this is a typical design problem. That's the floor system, and because that, and what we need to do is figure out how much steel goes in that floor system. Exactly. We don't know that yet. And it's not even so much that. A lot of what determines whether or not you have a rectangular cross-section versus a true cross-section is not so much the steel that goes into it, but the proportions. Let me put it like this. Let's keep in mind a rectangular T-beam versus a true T-beam. The difference is where the neutral axis is. Now, imagine you have a 2-inch thick slab versus an 8-inch thick slab. That's going to change things up a little bit. And that doesn't really have anything to do with the steel as much as it is just the geometry of the T-beam itself. Do you see what I mean? And the only way to figure that out is to really just sort of go through the math and work it out. From a simplicity standpoint, what makes the most sense is to start off assuming rectangular, then go back and see what's going on. Does that make sense? All right. Any questions? Don't worry, we're going to get plenty of practice, and I think the practice will make your life a little easier. Now, this is an example we're going to look at now. Just so you're aware, this box up here on the right, I threw this here because sometimes when you print these off, these numbers can be a little small. So this and this are the same thing. It's just blown up a little bigger so you can read it. We're going to design reinforcement for the floor system that's shown for an interior T-beam. So we have 4 KSI concrete, we have 60 KSI steel, we have 1 kip per foot superimposed dead load and 2 kips per foot live load. Now the beams are 20 foot long, so everything here is uniformly distributed loads, so we can use WL squared over 8. That'll make our lives a little easier. We have a floor system where the beams are 10 foot apart. The webs are 12 inches, 12 inches in width. The flange height is 4 inches. We have an effective depth of 18 and a total height of 21. Does that make sense? Any questions? All right. Let's see what happens. Okay. Okay. Now, I'm lazy. Okay, I think that's legible. That's not too bad, is it? Okay, now remind me, let's see, our other parameters. FC prime, 4 KSI. We had goodness. Fy is 60 KSI. We had a length of 20 feet. We had a live load of 2, right? Okay. Okay. All right. So far, so good? Okay. So help me out. First step, generally, is to compute MU, factored moments. Compute MU. You tell me what to do. Okay, so WU, right? WU, right? So we have 1.2 times the dead plus 1.6 times the live and all that. And then take that WU and then do what with it? MU is L squared over 8. What's the problem with that? Okay, how would we calculate our factored load, our WU? We take 1.2 dead plus 1.6 times live. What's the dead load? Somebody said 1 plus the self-weight, right? What's the self-weight? We haven't done that yet, right? Okay. All right. So, we'll need your help with this, all right? So, what's the self-weight? Like, how do we determine the self-weight of a T-beam? I want you to walk through this in your heads. Like, how do we determine the self-weight of a beam, period? No, you said volume times unit weight, but that'll give you the total weight. I'm talking about weight per foot. Unit weight times what? The area. The area. So, what are we missing? B. There we go. There we go. Now, we're going to calculate B, but I'm going to show you something here in a second how B actually isn't quite the answer. But we need to compute B anyway, so let's just go ahead and compute B. So, effective flange width all right, so tell me what to write. How do we compute B? Say it again.
L over 4 for assumption.
BW plus
16 times HF.
and then S. I like to put the little serifs on my S so that you can tell it's not a 5. So minimum. So instead of 20, so tell me what to write. Somebody else. So, but it's not 20, it's 20 feet divided by 4. So what's the answer going to come out to be? Feet, right? So why don't I go ahead, nope, multiply by 12. I thought you said divide. Never mind. Never mind. So BW is what? 12 inches plus 16 times, what was 4? And S is 10 feet or 12 inches per foot. What does that come out to be? Well, let's do each one. So the top one, 20 divided by 4 is 5. 5 times 12 is 60. 12 plus 16 times 4. 16 times 4. Yep. And this one is 120. So this is 60 inches. Does that make sense? All right. Any questions? Yes.
So after distance
I'm getting to that. I'm not done. Give me a second on that. All right. Is everybody okay with this calculation? All right. Now, he's raising a really good point here. Okay. This distance, this is the effective flange width. Okay. Now I'm going to sort of cross this out for a second. I'm going to say that B is 60 inches. Okay. Now I want everybody to have a crystal clear understanding of what B is. Okay. B is how much of that slab we are considering effective in resisting load. Okay. In other words, if I put force on that beam, how much of that slab can I consider to be effective in transferring load to that beam? And I'm saying 60 inches. Okay. So I am also saying over here 60 inches and over here 60 inches. So far so good? Okay. Now, so let me shade in this. Okay. And let me shade in this. Let me shade in this. Okay. Now the question is, what about this sort of shaded no man's land here in the main part of the span? Okay. What do we do with that? What do we do with this blue part of slab right here? What do we do with that? No. We don't put another beam under there, because I think you're confused in saying that slab isn't effective just as a floor slab on its own.
You're assuming that there's steel going this way?
Yeah, I'm not assuming there's steel going this way. I know that there's steel going this way because homework 3 or the third problem on the last homework assignment, you're designing steel to go that way. So it's not like that slab isn't reinforced. It is. But the question is, what do we do with it? Okay? Here's the answer. Okay? From a resistance standpoint, I can only consider the red portion for phi mn. Okay? I can only consider that for phi mn. But from a load standpoint, that blue slab has got to go somewhere. Okay? It's not floating there in space. So I propose that blue slab has got to be held up by the beams on either side of it. Does that make sense? I'm not saying it's not going. I'm not saying that we get it for free. We don't. The T-beams have to hold it up. They don't get to benefit from it from a resistance standpoint. Does that make sense? Everybody okay with this? Okay. Here's a simple way of going about this. Okay? All right. Help me out. Let's just keep this simple. Okay? How would I compute the area of this girder? We'll keep it simple. Let's look at the red portion for now. How would we compute the area of this girder? Don't write anything down just yet. Just bear with me. How do we compute the area? Well, let's keep it symbolic for now. So keep going. B times HF H minus HF times BW. Would everybody agree with this? Okay. Now, let's take this one step further, just in our heads. Okay. We would take this area, and we would then multiply it by 150 pounds per cubic foot to get the self-weight of the beam, right? But that would only be giving us the self-weight of the red portion, right? The blue portion is just sitting there, right? So here's what I propose. I propose that. Okay? So what I've done is I took that B dimension and I replaced it with the girder spacing. Why did I replace it with the girder spacing? Because the girder spacing, halfway over and halfway over, that T-beam is responsible not just for its own self-weight, but the self-weight of that slab that's hanging out in space. Does that make sense? No, go ahead. What? No, no. Finish that out. Remember,
Like the S only covers halfway between the two and the
what I'm saying is this. I'm saying that this T-beam in the center is responsible for this. Oh, goodness. And then the next T-beam over is going to be responsible for the other half and the other half. See what I mean? So what I'm getting at, we don't get to count on that blue slab for resistance, but we have to count on it for load. Does that make sense? Yes. But remember, that's already converted as a line load. So it's already 1 kip per foot just on the beam. That's a great question, but we don't have to worry about that because it's already on the beam. But in general, if you had a pressure load, it would be pressure load over what? Tributary width? What is the tributary width? It's the beam spacing, right? Does that make sense? Is everybody okay with this? These are good questions. Everybody good? All right. So help me out with this. Let's keep on calculating. So what do we have? We have, what is S? 120. Let's keep it in inches. So 120 inches times 4 inches plus 21 inches minus 4 inches times what? 12? What does that come out to be? Say it again. Do I have a second on that? So would you agree that that's how much load that beam has to hold up? Or that's what it's responsible for? All right? So the self-weight is that, right? So 0.15 kips, bless you, per cubic foot times 684 inches squared times what? Or what do I got to do to this? Yeah, 1 foot squared. All right, and that equals what? Say it again.
0.7125.
Do I have a second on that? Okay. So then our factored load is 1.2 W naught plus WD plus 1.6 times WL. What was our dead load, the superimposed dead load? It was 1? So that's 1.713 kip per foot plus 1.6. Oh, come on now. That looks like 1.6 times 2 kip per foot. And that equals what? Say it again. Second on that? Okay. And then MU is W. Oh, goodness. That was not good. All right, and then that's 5.26 kip per foot times, what was L? 20 foot. See, this right here, this is a perfect reason why you want to make sure that you're including your units, because you got feet here, but your girder spacing's in inches. Like, write out your units, man. It'll make your lives a lot easier.
So when did we do the 1.2 moment setup? Like, you know, how we did instead of the W's, we did it for the moments.
Like, when do you do, when do you separate it? That's a great question. Here's when you separate it. You separate it when this is your dead load and that's your live load. Because this is a distributed load, this is not.
Okay.
And if you try and take this and turn it into a distributed load to do this, I'm going to ask you to do that, and I'm going to go, bad. The reason why is because I know it's tempting to think that, oh, well, I can just take this and turn it into a distributed load and it's all the same, right? Well, it's all the same when you look at the reactions. But bending moments are not just the reactions. They are the distribution of force. They represent the distribution of load across the whole beam. If you try, like, just try it out. Take a 30-foot long beam, put like a 2 kip per foot distributed load on it, and draw the moment diagram. Then put a 60 kip load in the middle and draw the moment diagram. They're not going to be the same. While the reactions might be the same, I promise you they're not. They're going to be different because it's about distribution of load. Yes?
If you're like a pressure load on a floor system, you couldn't, like, if you're looking at the moments of it, you couldn't collapse them up.
That's not what I'm, no. That's not what I'm saying. That's different. And the reason why is because those beams are sitting on those girders, and those girders are sitting on those columns. Do you see what I mean? So that you can do. That's fine. Now, whether or not if you're looking at a girder, you can idealize that girder as just seeing distributed load, or you can idealize it as seeing just point loads from the reactions coming into it. You will get differences on the moment diagram. I promise you. That is undisputed. Two things. Number one, if you have like 6 floor beams framing in, there isn't much of a difference. Like the numerical difference, it just isn't that much. Okay? And two, you have to look at not only what's your difference in moment, but what's your difference in shear. Actually, the differences in shear can tend to be a little more, and it's actually more conservative to just use distributed load. But we haven't even gotten to shear yet. So, yes.
When you're solving for W naught, where did you get the 0.15?
Okay, that is the unit weight of concrete. That is the unit weight of reinforced concrete. That, unless otherwise stated, that's what we're using like the whole semester. So, all right. Any other questions? Okay. Now, if the whole B equals 60 inches versus S or whatever, if that was a little confusing, I think what we do next is going to allay those confusions a little bit. I didn't get the bending moment. What is this? 263.0? Foot kips? Is that good? Okay, all right. Does everybody have all this? Okay. I think what we do next is going to it's going to clear all this up a little bit. All right. Can I go on to the next panel? All right. Okay. So help me out. What's step 2? Now, you're both sort of saying the same thing. Okay. So you said compute MN, but you said, what'd you say? To compute MN, we need a phi value, and right now, what do we need to do? We need to assume that phi phi is 0.9. Now, I say it's assumed because we don't know what our steel is, we don't know what the reinforcement is, or we don't know what that is, so we don't know what the resulting strain is in our steel, so we got to just guess. All right, so Mn, now I should put Mn required. Mn required, goodness, I'm getting ahead of myself, is Mu divided by phi, which is, what was it on the previous panel? 263. Divided by 0.9 is what? I'm not even looking at the notes anymore. I'm just doing it live. 292.22 foot kips. And just for the heck of it, what's this in inch kips? We're going to need it. Okay. Now what's step 3? There you go. So we're assuming a rectangular beam, and using that assumption, what are we computing? Well, ultimately, but what do we calculate in between? Rho. So we're computing required rho. And then we assume essentially what Mr. Fitzpatrick said, a rectangular T-beam. Okay. All right, so remind me, what is our equation for rho? There we go. You're exactly right. And what I was hoping you didn't say was 0.18 FC prime over Fy. Remember, the 0.18 FC prime over Fy, we only use that when we don't have a clue what the beam looks like at all. And it's a good rule of thumb to get started. Right now, 0.85 FC prime over Fy. Now, let's go ahead and finish this out. So it's 1 minus 1 minus. Now, 2 Mn required, but this is really important in this equation because watch this, it's 0.85 Fc prime, but times what? On the bottom here. Bd squared. See, that seems innocuous, but that's actually really important, and that ties into what we did on step 1. See, on the load side, we made that beam hold up all that slab. But this is a reinforcement ratio. This is where we're trying to determine how much rebar needs to go in that beam based on a B value of only 60 inches. Does that make sense? If we used B as 120 inches, we'd get less steel, but we'd be counting on more of the slab than we're allowed to. Make sense? So we're only using 60 inches here because that's all we can use. That's all that we can consider effective. So we've accounted on that for the load side, but not the resistance side, and that's the difference. So 0.85 times 4 KSI divided by 60 KSI, 1 minus 0.85, 4 KSI. What was B again? What was D? 18. Don't forget, that is squared. All right, say that again. Do I have a sec? Oh, goodness. Do I have a second on that? They're not trusting you.
I'll say. I got the
Okay. Look, I just wanted to discuss the motion. I didn't. All right, all right. Okay. Now watch this. Now this is what's nifty, okay? Our next step is, and this is new for T-beams, is to compute the resulting, that does not look like a U, the resulting A. Okay. Now we do that, it's a pretty simple formula, so A is rho FYD, or wait, no, yeah, over 0.85 FC prime. Okay, so let's be clear what we're doing. This, what was it, 0.00309? That's how much reinforcement we need to meet this load demand. Now what we're going to do is we're going to say, well, if we used that much reinforcement, what would A be? Let's see what happens. So this is 0.00309, 60 KSI times, and what's D again? 18? And then 0.85, 4 KSI. Now what does that come out to be? Say it again, 0.982 what? Inches. No. It's not inches squared because your KSI and your KSI cancel, and then it's just inches. That's a great point. That's why you write those units down. What does that mean? It means it is rectangular, right? What is the flange height on this beam? It's 4 inches. So the resulting stress block is like way shallower than 4 inches. So our initial assumption that this was a rectangular T-beam was in fact very appropriate and very correct. So what I'm going to write here is assumption was valid, and then say that A is less than or equal to HF, therefore rectangular T-beam. Does that make sense? That's important. That's really important. Because now if this had come out to be like 9.982, we'd be wrong, right? We'd have been dealing with a true T-beam, and we would like skip to, was it step 8 or step 9 or something like that? So we're good. So our next step is to go to step 5. And what is step 5? Compute AS. And AS required is just rho BD. And that is just 0.00309 times 60 inches, right? We're only counting on the part of the slab that's effective, okay? Only the 60 inches times 18 inches. Say it again. 3.34 square inches. Does that sound good? Any questions? What time is it? Whoa. We actually, yeah, it is 10:50. All right. So step 6. So hold on. We're actually done with this example. The only thing I would say is this. Help me out. What is step 6? Choose a reinforcement pattern that has at least much that steel. Analyze it to check your assumptions and move on. It's that simple, okay? So what I would do if I were you, just for the heck of it, go find a reinforcement pattern that works. If you want a little bit of extra practice, and I don't know how appropriate that would be for this problem since the number is so small, but maybe try and find a steel layer, or maybe try and find a pattern that has two layers of reinforcement. The only thing you got to be careful of is your minimum beam width. Like if you have 2 layers of reinforcement and you pick a pattern that, let's say, has 12 bars, you evaluate your minimum beam width based off 6 bars, right? Because you only have 6 and 6. Does that make sense? So just be careful on that. That's all I have got. Those of you that said you wanted to help for Engineering Career Day, I will probably send you all an email later on today. If you're still interested, let me know. We'll probably get started. Like I'm going to plan to be at the Student Center around 7:45 or so Wednesday morning. If you're helping out, I really appreciate it. And we will still have our review session at 10 on Wednesday. So I'm still doing that. That's all I got. See you all. Yes? What's that? Not for this, because that would only be for the slab, and we don't need to worry about that for this. Give me one second.